What is isothermal process? Isothermal process is a type of thermodynamic process. Isothermal process is a type of thermodynamic process. Isothermal process is a type of thermodynamic process in which the temperature the temperature under bracket capital T of a system remains constant. Isothermal process is a type of thermodynamic process. Isothermal process is a type of thermodynamic process in which temperature capital T of the system remains constant. For isothermal process or change, absolute temperature under bracket capital T remains constant. Absolute temperature of an ideal gas remains constant. Change in absolute temperature, that means dT will be 0, there will be no change in temperature. Product of pressure and volume, that is PV, remains constant, and dP by dV, that is the slope of isothermal curve, will have the expression minus P by V. dP by dV will be equal to minus P by V. That's why we can write dP by dV iso, that is equal to minus P by V. That means negative ratio of pressure and volume. dP by dV iso is equal to minus P by V. That is the slope of isothermal curve. Slope of isothermal curve. Now if we draw isothermal curve, that means we have to plot pressure in terms of volume of the gas. PV graph is the isothermal curve, and this curve denoted by violet color is the isothermal curve that has negative slope because dP by dV iso is negative, minus P by V. This is the isothermal curve, pressure versus volume curve or graph. Variation of pressure with respect to volume is isothermal curve. Specific heat of the ideal gas for isothermal change will have the expression C equal to 1 by mass dQ by dt. As dt equals 0, change in absolute temperature is 0. That's why specific heat will be equal infinity, where dQ is heat absorbed and dt is change in absolute temperature. That's why specific heat of the ideal gas will be infinity. Specific heat of an ideal gas, that is C equal infinity for isothermal change. And isothermal process or change is a slow process. That means isothermal process will be conducted slowly. Isothermal process is a slow process, and gas is enclosed in a cylinder. Gas is enclosed in a cylinder with conducting walls. The ideal gas will be enclosed in a cylinder with conducting walls, so that there will be exchange of heat energy. Work done in isothermal expansion. Will have the expression W will be equal to nRT1 log base C V2 by V1. The expression of work done in isothermal expansion is given by W equal nRT1 log base C V2 by V1, where T1, capital T1 is the initial absolute temperature of the gas. Work done in isothermal expansion has the expression W equal nRT1 log base C V2 by V1. Log base C V2 by V1, and we can draw obviously initial and final state of the ideal gas. P1, V1, T1 are the initial pressure, volume, and absolute temperature. E1 is the initial internal energy of the ideal gas, and dQ is the heat energy absorbed by the ideal gas. As the gas absorbs dQ amount of heat energy, its pressure changes to P2, volume changes to V2, but absolute temperature T1 remains constant, internal energy remains constant, and N is the number of moles. In this case, pressure P2 will be less than P1, and volume, as the gas expands volume, final volume V2 will be greater than V1. Work done has another expression, that is W equal nRT1 log base C P1 by P2, initial pressure by final pressure. Since we know that according to Boyle's law, P1 V1 is equal to P2 V2. That's why V2 by V1 will be equal to P1 by P2. And third expression of work done in isothermal expansion of an ideal gas will be W equal 2.303 nRT1 log base 10 V2 by V1. This expression in terms of log base 10. We know that log base Ex is equal to 2.3026 log base 10 x. That means log x base e is denoted by ln x will be equal to 2.303 times of log x. Ln x is log x base e and log x is log x base 10. So these are the expression of work done in isothermal expansion of an ideal gas. Log base x base e is equal to 2.3026 times of log x base 10. Examples of isothermal process. Change in phase such as melting or evaporation. Change in phase such as melting or evaporation are also isothermal process. Change in phase such as melting or evaporation are isothermal process. Some parts of Carnot cycle. Some parts of Carnot cycle of a heat engine. Some parts of Carnot cycle of a heat engine. Some parts of Carnot cycle of a heat engine can be assumed as isothermal process. Now we can draw Carnot cycle. In isothermal curve. So this is the Carnot cycle which is shown in isothermal curve. A, B, C, D are the different different points in Carnot cycle. From A to B, the ideal gas absorbs dq amount of heat energy. From A to B, the ideal gas absorbs dq amount of heat energy. Temperature of the gas at A is T1 and the absolute temperature of the ideal gas at the point B is T1. Now from B to C, temperature of the gas changes from T1 to T2. At C, the temperature is T2. And along CD, the gas rejects dq amount of heat energy. Temperature of the gas at D will be again T2. From A to B, temperature remains constant. That's why the AB, that is expansion of the gas along the path AB, is isothermal expansion. Similarly, the expansion of the ideal gas along CD will be isothermal compression. The process of increase in volume or decrease in volume. The process of increase in volume, that is decrease in pressure along the path AB. The process of increase in volume or decrease in pressure of an ideal gas along the path AB or CD. Along the path AB is an example of isothermal expansion. Similarly, the process of decrease in volume or increase in pressure of the ideal gas along the path CD can be assumed as isothermal compression. Third example of isothermal process, that is slow expansion of an ideal gas enclosed in a cylinder with conducting walls. Slow expansion of an ideal gas enclosed in a cylinder with conducting walls. Slow expansion of an ideal gas enclosed in a cylinder with conducting walls can be assumed as isothermal process. Is an example of isothermal process. Slow expansion of an ideal gas enclosed in a cylinder with conducting walls is an example of isothermal process. This is a cylinder which encloses some amount of ideal gas. The cylinder fitted with a frictionless piston encloses some amount of ideal gas, and P1 V1 T1 P1 V1 T1 E1 and Q1 are the initial pressure, volume, temperature, internal energy and heat energy of the ideal gas enclosed in the cylinder. These walls are conducting walls. So that the gas will exchange heat energy with the surroundings. Now dQ be the amount of heat energy absorbed by the ideal gas enclosed in the cylinder. dQ is the amount of heat energy absorbed by the ideal gas, and the piston will move upwards, and there will be upward displacement of the piston fitted with the cylinder. Due to this, pressure and volume changes to P2 V2, but temperature and internal energy will remain constant as T1 and E1. Q2 is the final heat energy of the ideal gas. N is the number of moles. Here V2 will be greater than V1, P1 will be less than P2, and Q2 will be greater than Q1. And in this case, temperature remains constant. Initial temperature was T1, and in this final state, the temperature will be again T1. That's why temperature under bracket T1 remains constant in this isothermal expansion. And here P2 is the final pressure of the ideal gas in the final state. And temperature in the final state will be again T1. Initial temperature was T1 and final temperature is again T1. That means temperature remains constant. Similarly, internal energy will remain constant. Here temperature T1 remains constant due to this isothermal expansion, and here temperature remains constant. And internal energy was E1. Now final internal energy will be again E1. That means internal energy also remains constant. Internal energy also remains constant under bracket E1 also remains constant. That will not change. Internal energy will not change because temperature remains constant in this isothermal expansion of the ideal gas. Therefore, slow expansion of an ideal gas enclosed in a cylinder with conducting walls is an example of isothermal expansion, and the gas expands slowly so as to allow the exchange of heat energy between the gas and the surroundings.